Section 5.9 is volume by plane disk slices. Your essential question, given a solid whose cross-sectional area varies along its length, okay, meaning it's not just like a rectangle, okay, or a block or a cube, okay, it's something that, for example, looks like what we're going to do today, right? So this cross-section is going to end up varying, right? Its height is going to vary as its length changes. Okay, that's what we're talking about. How do you find its volume? By slicing it into slabs. So we're actually going to slice it up into slabs, or I call them discs, okay? And perform the appropriate calculus. So hopefully you're thinking to yourself, well, the appropriate calculus, let's see, I want some area under a curve here. Actually, I want some, not only area, I want some volume under this curve, right? Because it's three-dimensional. So probably if you relate this back to area under a curve, we're going to need to do some definite integrals from one spot to the next, so along the height of this. Okay, so that's where we are, and we are going to actually start by doing this exploration to help us get into understanding what the heck is happening. All right, so for this solid, because this is actually, so you have to, kind of use your imagination here. This is a solid, okay? Imagine, I don't know, this is somebody's head. That's like a cone head. Do you guys remember the cone heads? So this is somebody's head, okay? So it is solid, and we're looking for the volume of it. All right, so what it's telling us here is, we're going to draw a region. We're going to slice a strip that's basically perpendicular to the, this is important, perpendicular to the axis of rotation. So if I'm rotating my solid around the y-axis, then it's important that my strip that I draw is perpendicular to the y-axis. However, there will be other ones where maybe I took this solid and I rotated it around the x-axis. Okay, in which case it would be important that my strip that I draw is perpendicular to the x-axis. Okay, so then we're going to rotate the region and the strip to form a solid. And then the rotating strip forms a flat disk. That's basically what happens, right? If I take this strip and I rotate it around, I'm going to end up with this disk. Okay? All right, so let me just clarify a little bit for you guys. Last lesson we did two different examples where we were finding areas under two different curves, right? Or between two different curves. So this was problem 18 from 5.8. And I just want to draw your attention that, when my strip was drawn this way, and my width was dx, right, because this is perpendicular to the x-axis, so my width is dx. Well, it's important then that I multiply it by the functions in terms of x. So you can see here how I have x's times dx. It would not be appropriate to have, my functions in terms of y and then multiply it by dx. Moving on, that same lesson we did 16, where now I drew my strip perpendicular to the y-axis. And you can see that when I did that, for this one it was really nice for us because it was set up perfectly. I plugged in my functions in terms of y and then multiplied by dy. So you can see the y matches the dy. So it would not be appropriate here to have my functions in terms of x and then multiplying it by dy. So they have to match. Okay, so I just wanted to remind you of that, or maybe really point it out, because I think our last lesson I wasn't really trying to point that out too much. I was just trying to get you guys accustomed to drawing that the strip and then getting that into a definite integral. Okay, so now that takes us to this. So we have the region in quadrant 1, which is bounded by the parabola y equals 4 minus x squared, okay? And that's basically this right here, right? And I know that because my y-intercept is 4. If I were to factor this, I'd end up with in quadrant 1, I'd end up with a root of 2. Okay, it's rotated about the y-axis, so it's very important if I'm rotating about the y-axis that my strip is drawn perpendicular to the y-axis. And then it forms a solid paraboloid, okay, as shown above. Now, before I even go any further, what I can see here is that my strip, my width of this strip is along the y-axis, which means that my width then, and I like to turn it sideways, is dy. Okay, so when I'm all done here creating my integral, I'm going to end up with multiplying it by my width, which is dy. Okay, and I'm going to multiply that by some x. Okay, so my x needs to be my function, and because I'm multiplying it by dy, that function better be in terms of y. So I need to take this function and I need to solve it for x in terms of y. Okay, so I can then say, well, really, this is going to be, let's see, I'm just going to add x squared over. This is actually going to work out well for us, and I'll show you why in a second. Okay, all right, moving on to the first thing. Okay, a representative slice of the region is shown in the figure at the left. As the slice turns, it generates a plane disk, as shown in the figure at the right, right? So it's turning and it's creating this, basically it's like a circle, okay? But it's like a disc. I know we don't use CDs anymore, but maybe you still watch videos off of DVDs, so kind of think of it like that, only with a width to it, okay? So it's got quite a bit of width to it. It's got some kind of width to it, okay? So we're going to let xy be some sample point on the graph within the slice, right? So this is my xy. This is the point that I'm looking at. We're going to find the volume dv of the slice in terms of the coordinates of the sample point. Okay. The volume of this slice. So if I think about this, this is the volume of, basically it's a circle, but it's got a width there, right? Okay, so I need the area of the circle times the width of this. Now, what is the width? This shaded part right here. The width is going to be that dy, okay? And what is the other important thing is the radius. So what is the radius? Well, the radius is where I fall on this graph, okay? And that's basically going to be whatever my x is, okay? Now, that is why we solved for x originally. And the reason I didn't go ahead and get x completely by itself is because this is a circle, right? And so I need to be able to find the area of it, which is the radius is going to end up being squared, right? So the area is going to be pi r squared, right, of any circle. And actually the volume here then is going to be pi r squared times that width to get the volume, which is dy. Okay, so that's basically what we are figuring out right now. I kind of just did it for you. So really, dv, because we want the volume dv, okay, so we can make this a differential and then basically take the integral of it, is going to be that pi r squared times the width, or the thickness, okay? And again, your radius here is going to be x, okay? So radius is going to be x, which really means that radius squared is going to be x squared, in case if you're not following that, okay? All right, so dv will equal pi. Now radius is x squared dy. Okay, let's see, in terms of the coordinates of the sample point. So there we go. That's what we've got. All right, so by appropriate algebra, transform dv so that it is in terms of y alone. So no more x's. So this is why we transform this so that x was solved for, so that now it's in terms of y. So now I'm going to plug that in where I see x, and I'm going to have to square that, right? All right, so I'm going to end up with dv equals pi. Now I'm going to end up with 4 minus y squared. Oh, that's not true. I don't need to square that because that's already squared. I've got x squared that I'm plugging in, I'm sorry. And x squared is 4 minus y. So there's an error that hopefully you might have made, and now you'll see that you won't make it again. So that's in terms of y, and then if I wanted to, I can distribute that pi. So either one of those work. Okay, next we're going to find exactly the volume V of the solid by adding the volumes of the slabs and taking the limit as the thickness of the slabs goes to 0. So basically we're integrating. Okay, and we have a definite integral here because we are going to integrate. We know that this thing, the lowest it's going to go is 0, and the highest it's going to go is to 4, right? So those are our limits of integration. Okay, so we are going to say, well, this thing then, or the volume, will equal the integral from 0 to 4 of 4 pi minus pi y dy. And I can go ahead and integrate that. So this is going to, now that's just a constant, or at this point, it will be a coefficient, right? So I can, taking the antiderivative of that, I get 4 pi y. And remember, it's dy, so that's fine. I can just leave my y. I don't need to chain rule that at all. Okay, this is again a coefficient, so I leave the pi. The y becomes y squared, so that means I need to divide by 2. And I'm going to integrate that from 4 to 0. Okay, so let's see. So plugging in 4 here, I'm going to get 16 pi. I'm going to get 16 divided by 2, which is going to be 8 pi. And then if I plug 0 in, these are both just going to become 0, right? So I'm done with that. And I just end up with 8 pi. Not bad. Okay, moving on. As a rough check on your answer, compare it with the volume of a circumscribed cylinder and with the volume of an inscribed one. Okay, what the heck? Well, this takes you back to geometry. So a circumscribed cylinder is going to be one that goes along the outside. So thinking about something like, well, pretend like I can draw. Right, so there's your circumscribed cylinder. And then with the volume of an inscribed cone. So an inscribed cone is on the inside, so it looks something like this. Okay, so I've got a circumscribed cylinder and an inscribed cone. So let's start with the volume. Well, and we can make a conjecture here. What do we think? The volume of this paraboloid is going to be somewhere between the volume of the circumscribed cylinder and the volume of the inscribed cone. So the volume of a cylinder is basically the area of the base times the height, which is pi r squared times height. All right, so it's going to be pi. Okay, your radius here, let's see, so on this, your radius is going to be 2, right? But on that cylinder, but we need to square it. Okay, and then your height, now I didn't do a very good job of drawing this, but basically this comes up to the top of this thing, which is at 4. So we end up with 16 pi units cubed. Moving on to the volume of the cone. Now the volume of a cone is just actually 1/3 the volume of a cylinder. So it's going to be 1/3 pi r squared h. Okay, so this is actually going to be 1/3 of the 16 pi, or 5 1/3 pi units cubed. So comparing these two, and comparing what I got when I actually did the volume of the paraboloid, you can see it falls right in between. Okay, so I think that's what they're going to ask us next. Based on your answer to problem 4, make a conjecture about the volume of a paraboloid in relation to the volume of the circumscribed cylinder. Okay, so we know it's going to be less, because it doesn't take up as much volume, obviously, as the paraboloid. And it takes up more volume than the inscribed cone. Okay, and then you can go ahead and answer this. Hopefully you learned, the thing I really need you to get out of this is, did I draw this strip perpendicular to the x-axis or to the y-axis? And if I drew it perpendicular to the y-axis, then I'm going to have dy in my differential, which means that my function needs to be in terms of y. Okay, if I drew it instead perpendicular to the x-axis, then my differential will have a dx, and that means that this function better be in terms of x. We're going to add a little bit to what you just learned. What we just did was with discs, which are solid, okay? And now we're going to talk about washers. So this is where you can bring in like two functions, okay? Now a washer, in case if you're not too handy with construction, well, it would be more circular than that. But a washer basically has a hole in it, okay? So if I wanted the volume of this, and this thing does have a thickness to it, but I'm not gonna draw that right now. When you're finding the volume of this washer, you're gonna want to take, the volume of the whole thing, including this hole. So this hole right here is completely hollow. So this part here is solid. If you don't know what a washer is, look it up online. Okay, Google it. So we're going to want to take the radius of the whole thing, of the outside piece, basically, and I'll call that, radius 1, the first radius, or the bigger radius. And from that, what we're going to want to do is we're going to want to subtract out the inside piece, right? So that'll have a radius of R2. Okay, now these still have volume, so we have to, keep track of that. But it's going to be important to remember that you want to understand what is your first radius, what is your second radius. So basically, if I was finding the area, just right now, just the area of this, then I would want to do pi of R1 and square that. That'll give me the area of this whole thing. And then I'm going to subtract from that the area of the hollow part, which would be my pi R2 squared. Okay, now again, this is going to have thickness to it, so we're going to multiply all that by either dy or dx. All right, so moving on to number 8 on page 248. So this is a washer slices problem. Okay, this figure shows the solid form by rotating about the y-axis. Okay, so we rotated about the y-axis. Hopefully you're thinking to yourself, okay, well, if I rotate around the y-axis, then the strip that I draw better be perpendicular to that y-axis. Okay, and it's bounded by these two graphs, y equals x to the 4th and y equals 8x. We're going to find the exact volume of the solid using the fundamental theorem of calculus. Okay, you can assume that x and y are in inches, so when I find my volume, I should have inches cubed. And then I'm not going to do this to save time, but you can check your answer numerically by using Riemann sums. All right, so my two functions, first one is y equals x to the 4th. The second one is y equals 8x. Okay, and then I'm going to draw a rough sketch of this. It's not going to be perfect, but I am going to draw it. That way we have something to write on and reference. I probably don't need to be that big. Ooh, terribly done. But you guys have the picture in your book, so I would really focus on the picture in your book and not on my drawing. So this is the solid part. And what's happening here is that this inner part is hollow. Pretty terrible drawing. Thank you. Thank you. Okay. Now, hopefully you can look at this graph and you realize, yep, this is linear. So this right here is going to be my y equals 8x. And then this has a curve to it that looks like a parabola. So that's going to be my x to the fourth, or my y equals x to the fourth. Okay, so I'm going to go in here and I'm going to draw myself, oh yeah, a washer. Half the battle is drawing somewhat of a reasonable picture. Okay, so this washer then has an outside radius that we will call R1. So what is my outside radius? So my R1 goes to the outside function, which is my quartic function, right? So my outside radius right now, well, right now it's y equals x to the fourth. Maybe instead of putting equals, I'll put a little colon there because we're going to need to work with that. My inside radius, we'll call that R2. My R2 is going to come from the function, well, that's the linear one, so that's going to be y equals 8x. Okay, so now when I draw my strip, because it's being rotated around the y-axis, my strip is going to be perpendicular to the y-axis, which means that I have my width being dy. So if I'm going to write my dv, it's going to be whatever, the volume is times dy, or sorry, whatever the height is here times that thickness, which is dy. Okay, so my dy goes there, and I have to think to myself, are my functions in terms of y? They are not. So I'm going to need to put them in terms of y. Okay, so this one is going to become, well, I need to get rid of that fourth, so I'm going to raise it to the 1/4 power. So now I get x equals y to the 1/4. Okay, and then here I'm going to need to, again, solve for x, so I'm going to get x equals y divided by 8. Okay, so when I think about now my radii, okay, my R1 is going to be y to the 1/4, and my R2 is going to be y to the 8th. Okay, and that's what I'm going to plug in here. Okay, oh, and actually there's a pi in common, so I really could just factor out that pi. So I think I'm going to do that. Let's give myself a little bit more room here. I'm going to factor out pi. And then I'm going to do R1 squared, which is the y to the 1/4, but I need to square that. From that, I'll subtract the second radius, which is going to be y over 8, and I'm going to square that. So simplifying this, dv will be pi times, that will be y to the 1/2 minus y squared over 64 dy. Okay, so far I've written my differential. Now I'm going to need to write it as a definite integral. Okay, so my volume is going to be a definite integral. Now the question is, what are my limits of integration? So I need to know, where do they meet here and where do they meet here? So in order to do that, I'm going to go ahead and set these two equal to each other. Okay, so I'm going to take x to the 4th equals 8x Okay, I'm going to put them next to each other, set it equal to 0. I'm going to do some factoring. This is going to give me the x values, and I'll have to figure out what the y values are. I never thought we could have maybe done it with these, set these two equal to each other. I'm going to go ahead and just continue where I am. So x to the, I can factor out an x, so I'm left with x cubed minus 8. So x is going to equal 0. X cubed is going to equal 8, or in other words, x will equal 2. Okay, so when x is 0, well, just going back to these, when x is 0, y is 0. And when x is 2, y is 16. So I know that this point here is 2, 16, and this point here is 0, 0. So my limits of integration are going to go from the smallest y value up to the highest y value, okay, which they basically cross at 16 there, the y-axis. Okay, so from 0 to 16. And I'm just going to go ahead and write my Okay, now I'm going to take that integral and I'm going to evaluate it. Alright, so the pi I'm just going to leave out because that's a coefficient. Y to the 1/2 will become, oh, and I better put brackets there. Y to the 1/2 will become, well, y to the 3/2, and I need to divide that out, so 2/3, minus, now this is also going to be a coefficient, right? 1 over 64. And I'm going to have y cubed, and I'd have to divide that out by multiplying by 1/3. And I'll evaluate that from 0 to 16. Leaving the pi out there, let's see, 2/3, and then I'm going to have times 16 to the 3/2, minus 1 over 192. Okay, now let's see, 16 cubed times 16 cubed. And then from that, I need to subtract 0, but if I plug 0 into both of these, I'm just going to get 0. So this probably is where we pull out the calculator. Let's see, let's do a little bit more math here, see if we can make it a little bit easier. 16, the square root of 16 is 4. Cube that, that's 64. And 64 times 2 is 128. So I'm at 128 over 3 minus, oh yeah, I'm not even going to do that. 16 cubed over 192, and then times that by pi. And when you're all said and done, you're going to get approximately 67.021 inches cubed.